So in this module for qualitative data, we'll talk about visuals and numerical summaries. We're going to go over how to characterize and communicate information about the relationship between variables. And then we'll touch on good graph techniques and misleading representations. So good versus bad. So jumping straight into it, the very first visual that we'll want to cover is called the frequency table. There isn't a lot to it, but a frequency table will do a lot of the heavy lifting for us, even though it's not super exciting. There's not a lot of moving pieces. In the very first column of this frequency table is the name of the qualitative variable here, company. And underneath that are the different values that we have for that variable. Yellow Cab, Uber, Lyft, Via, and Juno. These are the different ride options people listed that they took. In the second column are the frequencies of how many people took each. So there was 12.6 million people who took the Yellow Cab, 4.8 million people who took Uber, 870,000 that took Lyft, 440,000 took Via, and just under 150,000 took Juno. And finally, the last column contains the percents by taking the frequencies and dividing them by the total. Now in this table, we have a breakdown of all of the possible values for the variable company and how often each one of those occurred. When we have those two things, we call this a distribution. So although this is a frequency table, we would also call this a distribution. To show you how a frequency table can be a very effective tool, I want you to think about the Super Bowl. In 2022, the Rams took on the Cincinnati Bengals, and they had over 100 million viewers. The Super Bowl is by far the largest sporting event in the country. It's one of the largest in the world, next to the World Cup. Now, because there's a lot of viewers, it's a really good opportunity for businesses and companies to air out ads to sell what they're trying to sell or show off products that they've got on hand. Now, in that Super Bowl in 2022, a 30-second ad was over $6 million. That's about $250,000 every second. So these companies wanted to say something, they had to figure out a short way to do it. Now, companies got so good at making these little commercials that some people started watching the Super Bowl just for the commercials. So this was a poll for 40 people asking them what their intentions were when watching the Super Bowl. Were they not going to watch? Were they going to watch for the game? Were they going to watch for the commercials? Or they didn't know. Now, if I asked you what the most common response was, like what are most people going to do for the Super Bowl? That's not a complicated question, but it's actually quite difficult to answer given a table like this. So go ahead, pause the video and see how long it takes you to answer that question. And if it takes you longer than 1 to 2 minutes, then we probably should be using a different graph or visual to answer that question. Instead, making a frequency table where we would list all the different answers, count up each answer, and then find the percents for each would allow us to answer this question immediately. So here's what that frequency table would look like. This is the distribution of the responses. And now it's very easy to see that most people were going to watch for the game. That's 18 out of the 40 or 45%. The second most said they aren't going to watch, and 8 of them said they're just watching for the commercials. Now, the question was difficult initially, not because it was a hard question, but because counting up 40 responses is actually quite time consuming. But oftentimes we'll be dealing with thousands, tens of thousands, or even millions of rows of data. So counting is no longer an option to begin with. Now, as we walk through these graphs that we're going to be using from here on out, I have these what I call 3 rules of data analysis that I want you to keep in mind. Rule 1 is to make a picture. And I think just the frequency table alone is proof enough to show you how useful a picture can be. It doesn't have to be elegant. I mean, a frequency table surely isn't elegant, but it's efficient and effective at answering even the most simple questions. Rule number 2 is to make a picture. Not only is it making it very easy to answer the simple questions efficiently, but sometimes a display will do a lot of the work for you. If you have a good picture to go along with your data, sometimes the viewer can answer their own questions just by looking at the picture. And rule 3 is to make a picture. I can't overstate it enough. Pictures are worth their weight in gold. They allow us to answer the easy questions. They obviously will answer a lot of the questions for us without doing any work. And pictures are usually the best way to report or communicate to others what you find. If you were presenting data to somebody else who's not working on the data with you, they're not going to want to see your Excel spreadsheet. They want to see a breakdown of what the data looks like in a table, a graph, something visual, something easy to digest. The next two visuals I want to talk about are related to each other. The one here on the left, we would call a bar chart or a frequency bar chart, and the one on the right is called a relative frequency bar chart. These two are very similar to the frequency table. The only difference is instead of showing the counts as numbers in the table, we will show the counts as bars, where the height of the bar corresponds to the count. The only difference between these two is the bar chart on the left uses those physical counts, whereas the bar chart on the right uses the percents. One thing I want you to notice is that the features or the characteristics about the bar chart, how the orange bar is always the tallest, the green bar is always the second tallest, and there's this downward trend. Those trends don't change whether you use the counts or the percents. Now in these charts, I have again all of the possible answers for whether people were going to take Yellow Cab, Uber, Lyft, Via, or Juno, and I know how many people took each. So these are both examples of distributions. Two more graphs that we won't work with too much directly, but do show up quite often, are the mosaic plot and the pie chart. Both of these graphs accomplish the same goal. They use a shape cut up into pieces to display the size of the categories. The only difference is the pie chart uses a circle where the slices are the categories. So bigger slice means bigger group, smaller slice means smaller group. The mosaic plot uses a rectangle where the biggest rectangle is the biggest group and the smallest rectangle is the smallest group. The point of a graph or a visual is simple: to effectively and efficiently display information that is easy to digest for anybody looking at it. It might be tempting to make it flashy, like if you take a bar chart instead of bars, you use pictures. It's more visually appealing, but doing so can really skew what the data is telling you, unintentionally or intentionally. In this chart, I've swapped out the bars for pictures. So instead of bars, I've got pictures of a yellow cab, a black Uber vehicle, and vehicles for Lyft and Juno as well. Now, the counts and the percents for that matter between yellow cab and Uber are a difference of 2.6x. That is, yellow cab had 2.6 times as many rides as Uber did. So when done right, the pictures of yellow cab and the Uber car should reflect that. But if you copy and paste that little Uber car into the yellow cab, you can actually fit just about 7 of those Uber cars in the yellow cab. That is, if you just look at the pictures alone, the yellow cab is about 7 times as big. So a reader might think, wow, there were 7 times as many rides. When really there weren't. There was only 2.6 times as many. The reason the scale of the pictures is different than the scale of the numbers is that the length of the cars is correct. The yellow cab is 2.6 times longer than the black Uber car. Unfortunately, so is the height. So you have a 2-dimensional difference. 2.6 times taller and 2.6 times wider gets you a 6.5x difference. Now, it's not to say that this was done on purpose or by accident. Most likely, it was done by accident. If you wanted this picture to be scaled correctly, what you would need is a really long, slender yellow cab that might look kind of awkward. So having the scale in both dimensions makes it more visually appealing. Unfortunately, it just does not match the scale of the numbers anymore. So a general rule of thumb is if you're the one making the graph, stick with bars, don't use pictures. It's difficult to get the scale right, and if you do get the scale right, the pictures usually aren't very visually appealing anyway. Now, if you see a graph that has pictures in it, that should raise a red flag to check to see whether the scale is correct or not. This is a bar graph that shows the average male height for 5 different countries, but instead of bars, it uses people because it's talking about height. Now, although the people do go up to the correct average height, because the people are scaled upwards and sideways, the scales of the people look a little awkward. If you look at the people in India, on average, the males are 5'5". If you look at the people in the Netherlands, their average height is 6 foot. Now that's a difference of 5 inches, but if you look at the pictures of the people, it looks like the people in India are half of the height, which is not true. If you look at the people from Indonesia, their average height is 5'2". But their person, the picture of the little person, only comes up to the knees of the people in the Netherlands, which is also not true. Their height difference on average is only 8 inches, 5'2" versus 6 foot. Again, this is not a matter of intent. It's just a matter of they used pictures, and to make the pictures look visually appealing, they had to scale them sideways and up and down. But doing so, it makes the scale a little bit different than what the actual numbers show. Looking back at the people in the Netherlands and the people in Indonesia, their ratio of 1.16x difference, that is 72 inches to 62 inches, is a 1.16x difference. Not a 5x difference, where if you took the small picture of Indonesia people and copied and pasted to make it the size of the Netherlands person. So if you have one categorical or qualitative variable, you could use the frequency table, you could use a bar chart with percents or counts, or you could use the mosaic plot or the pie chart. We have options, but they all only use one variable. What if you have two? What is our frequency table for two variables? Another version of that ride-sharing data is this table here, where I have it broken down by two variables. One, what country the people are from, and there's a whole list of countries here. And then not which ride-sharing app they used, but if they used one at all. So yes, they did, or no, they didn't. Each cell within this table tells you the count of that particular combination of either yes or no and which country they are from. So in the top left, that 845 is the number of people who are from Denmark and said, no, I didn't use an app. Whereas that 135 in green is the number of people who are from the Netherlands and said, yes, I used an app. On the far right, as well as the bottom, are the totals of the respective variables. So on the far right are the total yes and total no, and we call that a marginal distribution. On the bottom, that would be the marginal distribution of countries, so how many total people are in each country. This kind of a frequency table that breaks down two variables at one time is called a contingency table, or a cross-tabulation table. It shows you how each variable is distributed along the other variable. When we had the frequency table for one variable, the last column was for the percents. We could calculate percents in this table as well, but it gets a little bit trickier this time. If you focus on the 250 in the middle, in red, that is the number of people who are from Norway and said, yes, I used a ride-sharing app. But if you wanted to make a percent out of that, you actually have three different options. If you wanted to divide that by the grand total of people, say 13,356, you could, and you would get 1.87%. If you just wanted to divide that out of the total people in Norway, 1,056, you could, and you would get 23.67%. If you wanted to divide that by the total number of yeses, 2,753, you could, and you would get 9.08%. I want you to notice that in these fractions, the numerator is not changing. It's the denominator that's changing. And it's not that one is right or one is wrong. It totally depends on the question you're trying to answer. Out of everyone who said Norway and yes, that's 1.87%. Out of the people in Norway, what percent said yes is 23.67. Out of the people who said yes, who said Norway, that's 9.08%. They are three different numbers answering three different questions. If you use the grand total, we call that a total percent. If you use the total from the column, we call that a column percent. And if you use the total from the row, we call that a row percent. As a similar example, I want you to focus on the 916 people who said we are from Greece, and no, we did not use a ride-sharing app. If you wanted to know out of everybody what percent said Greece and no, you would divide that by 13,356, which would give you 0.068 or 6.8%. If you wanted to know out of the people who said Greece, what percent said no, we didn't use a ride-sharing app, you would divide that by 1,036, which would give you 0.884 or 88.4%. If you wanted to know out of the people who said no, what percent said Greece, you would divide that by 10,603, giving you 0.086 or 8.6%. Sometimes when you make a contingency table in a software like Jump, not only will it give you those counts, but it'll give you all three of the percents underneath the counts. One question that we could answer using a table like this is seeing if countries are similar in the use of how they use these apps. So do these countries have similar percents of yes and no? Now, although you might be tempted to just compare the counts of yeses and nos across the country, that isn't necessarily a fair comparison. The reason is that if these countries have a different number of people, then you aren't comparing apples to apples. In order to make the comparison fair, we'll use percents instead. We'll look at the percent of yes and no for each country. The numbers that I've outlined here in red are the row percents for yes. That is, I totaled the number of yeses found in the right, and I divided each country's count for yes by that total. So these are only the yes responses. They have nothing to do with the no's. Now the numbers here in red are a distribution, but since they're only for the yeses and not the no's, we call it a conditional distribution. I have fixed one of the variable outcomes as yes, and look how the other variable changes, country. We call that a conditional distribution. To show you another question that we can answer using a contingency table, consider this smaller example, where I've made up some data about two variables: the number of students in two of my sections, section E with 70 students and section G with 35, and the sex of the students within that section. If I asked which section has more males, you might be tempted again to use the counts. And you would say, well, section E has 40, while section G has 29, so section E wins. And although that is right, 40 is bigger than 29, that's not really a fair comparison. Section G only has half as many students. So even if section G had 100% males, it still wouldn't have as many as section E. As a more fair comparison, I want to compute the conditional distribution of sex for each class. I'm going to compute the percent of males and the percent of females within each section. So for section E, I'll take 40 divided by 70, and I'll take 30 divided by 70, giving me 57% males and 43% females. Then I'll rinse and repeat for section G. I'll take 29 and divide it by 35, and I'll take 6 divided by 35, giving me 83% and 17% respectively. These are the two conditional distributions for sex in each of these classes. So to answer that end of the question, which section has more males, both of those things can be true. You would say that since the percent of males in section E is 57, and that's less than the percent of males in section G is 83, we would say section G has more males percent-wise. While it's also true that section E has more count-wise. Now, if you just look at the conditional distributions of sex for both sections, they are quite different. Section E is almost a 50-50 balance, while section G is overwhelmingly male. These conditional distributions are different, and when that happens, we say that the two variables, sex and section, are dependent on each other, because the conditional distribution you see depends on the section you look at. In this other example, where I've made the conditional distributions identical, that is, section E has 70% males and 30% females, so does section G. Section G also has 70% males and 30% females. These conditional distributions are now identical, so we say that these two variables, sex and section, are independent. That is, the conditional distribution you see does not depend on the section you look at. If you look at section E, you're going to see the same percent males and females as if you were going to look at section G. This is from a data set that displays types of cars, sporty, small, compact, medium, and large, and where they come from, Japan, other, or US. Now for every contingency table in Jump, there's an upside down red triangle in the upper left-hand corner. If you click that red triangle, you can select and deselect different things to be shown within the contingency table. Usually the first four, count, total percent, column percent, and row percent, are shown automatically. When I'm trying to figure out if two variables are independent or dependent, I will unselect everything except row percent or column percent. You can use either one. In this example, I've left row percent and count just so you can see how the counts change, but I'll specifically use row percent to tell if these variables are independent or dependent. Since I selected row percents, my table is showing the conditional distribution for each type of car. That is, in the first row where I have highlighted 40, 16, and 44, those percents are telling me out of the sporty cars, where do they come from? 40% of the sporty cars come from Japan, 16% come from somewhere else, and 44% come from the US. That is only just the sporty cars. I've marked the other 4 conditional distributions for small, compact, medium, and large in different colors to show you where they are. Now, to tell whether country and type are independent or dependent, I'm going to look to see if the conditional distributions for the different types of cars are the same. That is, I know that out of the sporty cars, 40% come from Japan, 16% come from somewhere else, and 44% come from the US. But is that also true for the other 4 types of cars? In this case, it's certainly not true. The conditional distributions for these types of cars are actually pretty different. Just looking at the sporty cars, most of them come from the US and Japan. But if you look at the compact cars, most of them come from somewhere else. And the large cars, most of them come from the US, the vast majority, that's 70%. Since the conditional distributions depend on which car type I look at, I say that these 2 variables, country and type, are dependent. If the 2 variables, country and type, were to be independent, then I would have to see the same conditional distribution for each type of car. That is, if I see 40 and 16 and 44% for sporty, I would need to see those 3 same percents for small and compact and medium and large. It does not mean that the 3% have to be 33, 33, and 33. It just means that the 3% I see in one row have to be the same 3% in every row. Now, the frequency table was for one variable, just like the contingency table was for 2. And so when we have a bar chart for one variable, we have visuals for 2 variables as well. So I'll show you a few of them here. The segmented bar chart is the first one I want to talk about. On the left here, I have a bar chart that displays 5 different sales strategies and the number of sales corresponding to each. But in this company, they also sell 4 different products. So I have segmented each bar to show how much of each product is sold within each strategy. So now looking at those segments, you can see that between strategy 1, 2, 3, and 4, the proportion of the segments within the strategies are about the same. Yes, they sell more product C than anything else, but it's not drastically more than product D or product B or even product A. As opposed to if you look at strategy 5, they hardly sell any product D, but between A, B, and C, there's really no big difference. We can still see, though, looking at the heights of the bars, that strategy 2, 3, and 4 sell the most product altogether. This next graph is the relative frequency or the percent version of the segmented bar chart. This shows the class preferences for students and teachers, where the 4 different classes were Intro Stats, Pre-Calc, AP Calc, and AP Stats. One of the drawbacks to a graph like this is that since it is a percent, that is, the students and the teachers both have their bars that go up to 100, it's hard to know, or even impossible to know without any more information, which group had more people. Yes, I can tell you that since the dark blue portion of the students was the largest for students, they like AP Stats. And since the teachers, the largest section was the light blue, the teachers like AP Calc. But I can't tell you how many that was. And I also can't tell you which group had more people. Were there more students or were there more teachers? An easy way to fix this, at least the second problem, is to make the width of the 2 bars different. That is, the width will now be proportional to the size of the groups. So if there were a lot of students in proportion to the teachers, the width of the student bars would be bigger and the teachers would be narrower. This graph is called a mosaic plot. That is, a mosaic plot is nothing more than a segmented bar chart by percent, but the width of the groups now represents the size of the groups. So here we can see the width of the student bars is roughly 4 times as wide as the teachers. So now we know that there are probably 4 to 5 times as many students as there were teachers. To show you one last example of contingency tables and how to tell if variables are independent or dependent, I want to talk about the Titanic. In 1912, the Titanic was this massive ship that pretty much had two goals. It was going to sail across the Titanic, and everybody was going to have a wonderful time while they did so. And one of the key phrases that floated around the Titanic was that it was an unsinkable ship. Unfortunately, on the night of April 14th, when it hit an iceberg and it sank. And it was in the Northern Atlantic. It was not a very good time. It was very cold. It was a pretty bad day in history. Now, since it was such a famous event, we have exclusive and a lot of data talking about the passengers, what kind of passengers there were, what class they were, and who survived and who did not. In this contingency table, I've got two variables: the class of the passengers, first, second, third, and crew, and then if they survived and if they didn't. To clean things up, I only left the counts and the column percents. I'm not showing the total percents, and I'm not showing the row percents. Now, since these are column percents, what I'm showing you are the conditional distributions of survival for each class. That is, in the first column, that 62 and 38% are the percent survival and deceased for first class only, and likewise for the second, third, and crew. If these two variables were going to be independent, then what we should see are the same percents of alive and dead for every class. It doesn't mean that it'd have to be 50-50 for every class. It just means that whatever 2% I see in one need to be the same percents I see in the other three. Now, as an example of why we look at the percents and we don't look at the counts is because these groups are very different sized. The first class passengers only have 324, while the crew members have almost 900. That is, yes, 677 of the crew members died, and that is terrible. But the first class passengers, they only have 324 to begin with. So in an instance where every first class passenger died, 324, they still wouldn't have had as many deaths as crew. So this isn't making it a very fair comparison by looking at the counts, so we look at the percents of alive and percents dead instead, taking into account the size of the groups. Now, in this particular case, these conditional distributions are not the same at all. The first class passengers, 62% of them survived, while third class was 25 and 23% of the crew. The survival rates would all have to be the same for every class, and so would the death percents. And they're not the same, they're not even close. So I would say that these two variables are dependent. The percents alive and percent dead depend on which class I look at. To wrap this lecture up, I want to show you some good graph techniques and some not so good graph techniques. And I don't think there's any better way to do it than to show you some examples right on the internet. And one of my favorite places to grab graphs like this is on social media, where there is a plentiful of exchange of ideas and graphs. This very first graph came from Twitter and the White House on December 16th in 2015, so not terribly old, but not super recent. And this graph was supposed to show that more students are earning their high school diplomas than ever before. Now, as a staunch advocate of education, I'm thrilled to see this. I love the headline, I love the point of this, but the graph, not so much. Number one, we've talked about that when you see pictures instead of bars, that should raise a red flag, because getting the scale right can be extremely tough. On purpose or not, getting the scale is hard without using just straight bars. And so here I'm seeing books instead of bars. I'm starting to think there might be something weird going on here. And when I look into the numbers, yeah, it sure seems that way. On the right-hand side, the stack of books goes up to 82%, while the stack of the books on the way left goes up to 75%. That doesn't seem like a huge difference, but the stack of books on the right is 3 times as high. Yet the percent on the right is not 3 times as that on the left. Now, the most common reason for a scale that is off like this is because the y-axis is not starting at 0. And there are some reasons why you might want to do that, and a lot of why you might not. But the fact that they don't show the y-axis here is not great. One should show the y-axis so the reader can understand immediately that the height of these bars is not quite right or what you might think it is. Now, fortunately enough, the source of this data is the U.S. Department of Education National Center for Education Statistics. It's a free source that anybody can go online and look up this data. This is not hard data to access. So somebody, I won't name names, went and grabbed this data and made this same bar chart, taking the pictures off and replacing them with bars, and starting the y-axis from 0. The bar chart you see on the right is the resulting graph. It contains the same exact data as the graph on the left. But again, with just no books, they're only bars, and the y-axis starts at 0. Now, for better or for worse, this graph does not tell exactly the same story. As much as I love education, if I wanted to show somebody a graph that would tell them how many more high school diplomas we've been giving out, the graph on the right's not really one I'd want to show them. Is it going up? Is there a trend going up? Yeah, there is. Is it more than ever before? Yes, it is. By how much? Maybe not as much as it would have seemed by looking at the graph on the left. This second bar chart comes from Twitter and the White House from 2022, talking about the economic growth since 1984 that we've seen. Now, this y-axis does start at 0, and I don't see any pictures instead of the bars, so those are two very good steps. But there was one alarming thing, and that is that if this is the best and strongest year for economic growth since 1984, as a reader, I want to know what happened in 1984. Now, not only does this graph not go back to 1984, but if you look at the y-axis closely, there is a bit of a discrepancy. The tick marks go up by 0, 1, 2, 3, 4, 5, 5.5, and then 6. That extra half might seem oddly inconspicuous, but when we make graphs in Jump or you make graphs in PowerPoint or Excel, these graphs are ticked automatically. That is, they are equally spaced automatically. You do not have to go in and make ticks like this, which means if you wanted to make a tick like this, you'd have to do it by hand. Now, making that extra half at the end does one thing. It makes bars in that region taller than the other bars. Not by much, but taller. This third bar chart is looking at the penalties called on opponents in the regular season in the NFL since 2022. And as a diehard Vikings fan, this graph pains me to look at, but for stats, we're going to go into it. Now, yes, they do use pictures on the top of the bars, but since the bars themselves don't contain pictures, I don't have any immediate problem with that. I do like the colors of the bars. It makes it very easy to distinguish between themselves since there are a lot of bars here, but they do not label the y-axis. Now you see the Vikings lead the pack at 363, while the Bears also lead the pack in the other direction at 263. But the height of the Bears bar is maybe an eighth, a tenth of the size of the Vikings, while the physical numbers are not that big of a difference. And again, that is because the y-axis likely does not start at 0, but we won't know what it starts at since it is not labeled. Now, just like the education statistics, NFL statistics are freely available, and so somebody could even hand code these right into Jump and make their own bar chart. So I've went ahead and done that and started my y-axis at 0, and that's what you see on the right. Yes, the Vikings still lead the pack, but you can see actually most teams have very similar amount of penalties since 2022. It's just not as exciting to look at since they're all about the same height. One thing I want you to notice is that Jump has automatically scaled this graph to go up to 400. Likely, that is because 400 is the nearest value to the highest value that is nice and even. But you can actually manually change this. If you wanted to make it look like no teams ever had any penalties ever, you could go ahead and change the maximum value on the graph to something much larger, say 4,000, which would in turn decrease the height of every bar in this graph, which would give you the resulting graph on the left. Not only does it now seem that every team has about the same number of penalties, but that they hardly get penalized at all. Now, if you're wondering, well, of course somebody's going to see right through that. They can see the labels on the y-axis. But if we just follow one of the patterns that we've seen in the last few graphs, easy fix. Delete the y-axis and no one will ever know. Now the only thing we're missing is a catchy tagline and somewhere to post this. This next graph is about violent crime between April 2021 and October 2018. But the very first problem with this graph is that the x-axis seems to be flipped. The next problem with this graph is that the time frames between the dates that are listed are not consistent. The time frame in between the first two dates is 10 months, between the second two is 15 months, and the last two is 5 months. Flipping the x-axis will reverse the trend. So if there was initially a trend down, flipping the x-axis will cause the trend to go up and vice versa. When the time frames are different lengths, that can tend to either increase the steepness of the trend or flatten the trend out, depending on if the time frame is being elongated or shortened. Now, when you flip this x-axis reading from left to right, and you make the time frames equally spaced, what you get is still a trend, but a trend that doesn't seem quite as dramatic. One that still goes down and then back up, just not in such a dramatic fashion. This next article by the New York Times describes the amount of judgeships that were appointed by previous presidents. And so on this next slide, they show a graph to display that information, but there are some initial problems with this graph. It appears that they're trying to use a bar type graph, which is not a problem, but they are using pictures for the bars, which I generally recommend against because getting the scale is extremely difficult. Now I'll give them credit where credit is due. They don't change the scale from left to right. It is literally just the length of the gavels here that are changing. So if it's the height of the bars or the length of the gavels, it doesn't really make a difference. So that appears to be okay. But there is no y-axis here, so we don't know if the length of these gavels starts at 0 or something else. It does appear to me that it probably doesn't start at 0. The reason is because the fifth bar says that there were 15 judgeships appointed, and the next one, the last one, there was 24. So the difference in that scale tells me that if someone were to appoint 2, 1, or 0, I don't know how long or short that gavel would be. It would be non-existent on this graph. Now, because there is no y-axis and it appears to not start at 0, the difference between these gavels or bars seems to be a little bit misleading, in that the difference between 15 and 24 is about a 50% increase. But if you took the gavel on the fifth one, you'd probably need about, 6, 7, 8 of those gavels to make the last one? So the difference here is being exaggerated. I've recreated a similar bar chart with the y-axis starts at 0, and you can see the same trend, that the number of judgeships appointed by previous presidents seems to be maybe slightly down, more or less little constant, and then the last bar is the highest. By a huge difference or a marginal difference, that's up for debate, but the difference in the graph on the right is not as big of a difference that it is in the graph on the left.